For those of you who've arrived for the 3 o'clock class, if I could ask you to do me a favor, when the class is over, there's a big event afterwards, and people are going to be pouring into the back. So if you wouldn't mind leaving out of this door down here, that'd be really help with the traffic flow. Thank you.
Hello? Can you hear me? Is this good? Thumbs up if you can hear me. All right, cool. Oh yeah, same. All right. It is 3:10, so everyone settle down. We'll go ahead and get started. Quiet, please. All right, thank you. So a couple of announcements to start today. Homework 2 is now released, and it'll be due next Wednesday, March 15th, called Percolation. It's a pretty cool homework. And if you want, there's some optional spoiler videos and slides that Josh made for the homework. If you get stuck or you just kind of want a faster route to success, because the homeworks aren't really meant to make you struggle with them. They're meant to be enjoyable and give you experience with the material. So you can check those out. And also there is a Gorilla section tomorrow from 12 to 2 p.m. in the second floor. Soda as usual, so you can go and get some more practice with asymptotics. Now, Josh is unfortunately both sick and out of town today, so I will be filling in for Josh. My name is Ross, and Daniel, wherever he is, somewhere, there's Daniel, will take over halfway through, I think. Now, for this lecture, we're going to be doing a lot of manipulating some trees. So it'll be great if you have some paper and a pencil to work out some of these problems, because I think that's the best way to really understand what's going on. Hopefully you all still use the paper and pencil things. All right, so the topic of today is going to be balanced search trees. So today we're going to be giving you a bunch of clever techniques that you can use to improve the performance of binary search trees greatly. And in addition, it turns out that in this day and age, knowing how to balance search trees is becoming an important life skill in general. So, the next time someone asks you to balance a binary search tree, hopefully after today's lecture, you'll be wise enough to say, well, just use a balanced search tree. So let's talk about the trouble with our typical binary search trees. The problem is that BSTs can run into performance issues where they get very spindly. And by spindly, I mean in the case where your tree ends up being very tall. So, for example, this often happens when you are inserting items in order. Let's say we have a tree with a bunch of letters, and then we're just going to add the letters Q, R, S. If we put them into the tree, then they're just all going to get attached down the right side of the tree. And so we end up having this long line on that side of the tree that if we want to check if an element's in the tree, we'll have to go all the way down the height. And that's going to start taking roughly closer to linear time in terms of the number of elements in your tree if you're having to go through all these elements to find what you're looking for. And so the fundamental issue here is that we're being too lazy about where we store our data. So one potential solution is, well, why don't we just insert our elements in random order instead of increasing order? Now, we're not going to talk about the math here, but researchers have discovered that if you insert elements in random order, then generally the height of your tree will be logarithmic in the number of elements, which is good. So why don't we just do this? Why don't we just always insert our elements in random order? What's the problem with that idea? Yeah, right. So we don't always know what all the elements are that we want to insert. A good way to think about that is, let's say that you are using a tree to store your incoming emails, where the emails are sorted in the tree by how recently you received them. And as a teacher, our inboxes are basically always receiving new emails and always getting flooded. There is never an end to the emails. So you'll never reach a point where you know all of your data so that you can insert them randomly. So that's why we can't just insert totally in random order. So, but let's keep on this track of thinking how we can come up with a better tree. And the problem really boils down to is the fact that we are adding new leaves to our tree. The fact that our tree is getting taller and taller as we add new elements. So one naive solution might be, well, okay, let's just make sure that we never add any new leaves. That way the tree can never get imbalanced. Sounds good, okay. But then what do we do with incoming data? Now, the interesting thing here is that this idea that we don't add new leaves, this does not mean that we can't add new data. And this is where the tricks are going to come into play this lecture. So what we can do, and actually let me pose this question to you guys. So how can we add new keys into our tree without adding any new leaves to the tree? Let's go ahead and take 30 seconds, talk to your neighbor, and think about this. All right, who has an idea for what we can do? Any brave souls with an idea? Put them in a new tree. Okay, so that's one idea. We could just create a separate tree and start storing more data in that tree. And there are some places where that could be useful. But that's not the answer we have in mind. Yes? So we put P where O is. Then N would be the leaf. And then where does Q go? Q would go where P is. Okay, I'm going to go off that idea, that Q is going to go where P is. And essentially our solution is that we're going to stuff our nodes with more elements. So we're going to take Q and we're just going to put it inside the node that contains P. So here we've added more elements to our tree, but we haven't actually added any new leaves. So technically the height of our tree hasn't changed. And if we continue with this process, as we add more elements to the tree, then we'll just keep sticking them inside leaves. So if we then add the nodes R and S, they'll both just get stuck in this leaf. Now, this is sort of a logically consistent data structure, but it's kind of weird, right? Because if we want to check whether or not we contain, let's say, R, then what we'll do is we'll search first for the appropriate leaf, and then within that leaf, we have to figure out whether R is in that leaf. So what's the problem with this idea then? If we keep stuffing new elements into this leaf, what's the problem? That's right, yeah. We'd still have to search through this whole leaf to get that value. So if we take this idea to the extreme and we add a whole bunch of elements in order, then we're just going to add them all to that one leaf in the tree. And so we're really not doing any better than we were before, because we still are performing essentially a linear search through all of the elements inside this node. So the idea isn't perfect. So now we have a new problem, that our leaf nodes can get too juicy, as Josh would say. Or an analogy I would like to use is dolmas, where you take grape leaves and stuff them with rice and other things. Maybe your leaves, you're stuffing them so full that they're just about to burst. And so we need to figure out a way to make sure our leaves don't get too stuffed. So the goal here is that we still don't want to create any new leaf nodes, but we also don't want our leaves to get too juicy or too stuffed. So how do we solve this? For this one, I'm just going to give the secret away to you. So let's say that we want to set a cap on the number of items you can have in a leaf. So we're going to limit the number of items that can be in a leaf, let's say 3. So if our limit is 3, then PQRS has 4. That's too many. That's bad. So if a leaf gets more elements than the cap, let's just give an item to its parent, say the left middle. So here we're going to take our element Q and rip it out and bring it up into the parent node. And so then our parent node will contain OQ. Now, this creates another sort of problem, right? Because this node has 2 children here. And what does it really mean for something to be less than a node that contains multiple elements, or to be greater than something that contains multiple elements? So you might say, okay, well, left child could mean if you're less than everything in that node, and greater means, or right means you're greater than everything in that node. And that works for N, maybe. But what about P? Because P is greater than O, but it's less than Q. So does it really make sense for it to be the right child of this node? Seems kind of weird, right? So this is a very difficult problem to figure out how to get this idea to work, where we have a consistent and sensible notion of what it means to be less than or greater than this node. So I'm again going to pose a challenge to you. How can we tweak our idea to come up with a consistent idea for what it means to be a child of this node? How can we fix this? So take a minute, talk to your neighbors, and think about this. All right, so let's see what you all came up with. How can we tweak this idea? Yes?
So instead of moving Q up there, you can move P instead, and everything on the rightmost node will still be greater than everything in the parent node.
Okay, so that's an interesting idea. So you're saying that instead of moving Q up, we could move P up. And then in that way, everything in here will still be greater than everything in there. Okay, so for this example, that would work, true. But let's say that later in your tree, you wanted to add some element that was between O and P. So imagine that there was some letter that came in between O and P. I don't know what it would sound like. But if you were to insert that into your tree, you would run into the same issue of where would you put it. So it's a good idea, but not quite. Yeah?
With that idea, though, could you just put the element between O and P into that node? Like, into the node with O and P? Because it's still, like, less than 3.
So you could stick it into this node as well, but that may require checking your children to figure out whether it would be in the middle of the children. Our code could get pretty complex. Yeah. Make P its own node between O and Q. Now that is a great idea. Yes, that is what we're going to do. So the solution to this problem is called node splitting. What happens is when we take Q out of this node, you can think of it like we're reaching in and grabbing Q and ripping it out so hard that we're actually tearing this node in half, where P is going to become a separate node and RS is going to become a separate node. And then the way we attach those nodes to our parent is that now the parent is going to have 3 children, where the middle child represents all of the elements that are in between O and Q. Okay, so now we have a data structure that's consistent and not as weird. So if we want to check whether R is in our tree, for example, we'll start at M, see that R is greater, and go to the right. Then when we get to this node, we can first compare R to O and see that R is greater than O. Then we'll compare R to Q, and we'll see that R is greater than Q as well, and then we'll go to the right. Whereas if we were checking P, P would fall in the middle of O and Q, so then we would check down the middle child. So if we do this, it means, question?
What would you do if the parent node had more than 2 elements in it, and there were 2 possible ranges of intermediate values?
Good question. We're going to talk about that. So in this way, by examining a node, it's going to cost us z compares, where z is the number of elements in that node. But that's okay, because we've set some cap on z, some constant number to say that nodes can't have more than, for example, 3 elements here. So that's okay. It doesn't really hurt our runtime. Now, you might be wondering, well, what happens if another node that isn't a leaf gets overstuffed? Can we split that as well? And we'll talk about that soon. Question? So the question is, I thought we weren't supposed to make a new leaf. Now, to that I would say that we're not technically making a new leaf. It's just that we're taking a leaf we had and breaking it into. That's going to, it is a very useful property that we're going to talk about in terms of the height of the tree. Yes, I suppose that's sort of a technicality, sure. Okay, but first let me check your understanding. So suppose that we have this tree and we insert the letters T and U. Now if we do this, what is our tree going to look like now? So here this node is overstuffed, so something's going to need to move up, but then our parent's going to have 3 elements in it. So I want you to take 30 seconds or a minute and work this out and figure out what our tree would look like after we fix this node. All right, so let's see if this is the tree you came up with. So when we split this node and we propagate S up, we're going to get a tree that looks like this, where our parent node, when it has 3 elements in it, we're again going to split. So when we bring S up, we're again going to split this node into a node that contains R and a node that contains TU. And then our parent node is going to have 4 children now, where we have the elements that are less than everything in the parent, the elements that are between O and Q, the elements that are between Q and S, and then everything that is greater than S. Any questions on this? Yeah. How do you choose the S? So in general, we'll say that we'll always propagate up the left middle element. So the second element. Okay, now I'll show you what happens if we have a chain reaction of inserting. So let's say that we now insert the letters Y and Z into our tree. So this node is too full. We need to propagate an element up. So we will rip out U, we'll move it into the parent, and now we have this node that is also too stuffed. And it has 5 children. Can't have that. So what we'll do here is we'll just apply the same rule we've been applying so far to the parent node, where we'll rip out an element and we'll move it into its parent, which in this case is the root. So we'll take the element Q, we'll propagate it up to the root, and now the root is going to have 3 children. Now, let me ask you, what is going to be this node right here? What's that? Oh, they can't see the mouse. Oh, interesting. So here, what is going to be this node here? O, yes, that's right. So O is going to be the middle child of the root, and then it's going to keep the children N and P. And then on the right, we'll have the node SU, and it has children RT and YZ. Question?
How does the node O know to keep N and P and not just leave it at like S and U?
So the question is, how does the node O know to keep N and P? NP, right. So when we take Q and we break this node and we bring Q into the root, then we're splitting this node into O and SU. And since N, you can think of it as N was originally attached to the left of O, and P was originally attached to between O and Q, and so we just say that it was attached to the right of O. And so when we move Q up and we split this node, then P just becomes attached to the right of O, still being in the middle of O and Q as it was before. Any other questions? Yeah. So your question is, what happens if the root gets too full? Great question. That is my next slide. So I have one final challenge to pose to you, which is, well, what happens if the root gets too stuffed? So in this example, we have the tree where the parent has MQUW, 4 elements, and that is violating our rule for the tree. So our root is too big. So now, what are we going to do with this root? So let me give you guys another 30 seconds to think about this and decide what should happen to our root node. All right. Who has an idea for what we should do with our root node? Yeah. Okay, so the answer was we should take Q. Where's my mouse? We should take Q and split this node by ripping out Q and making Q the new root. Yes, that is correct. That's what we're going to do. So we're going to take the node Q, we're going to rip it out of our root and make it the new root of the tree. And its children will be M and UW. Now, this is sort of interesting because here we have added to the height of our tree, finally, which is something that we've been trying not to do. But what's different here is that instead of adding new leaves to the bottom of the tree, all we've done is add a new root to the top of the tree. And that has some very nice properties for our performance. Specifically, that splitting trees are guaranteed to have perfect balance. And let me explain that. So if we split the root like we've done here, every node in the tree gets pushed down by exactly the same amount. Every node's height is going to increase by 1 in the tree. But everything is increasing by exactly the same amount. And if we split a leaf node, or any other node that's internal to our tree that's not the root, the height of the tree hasn't changed. So if we then talk about our tree, where let's say that M is the maximum number of children that any node can have in our tree. And so that is always going to be 1 more than the limit for the number of elements in the tree, right? Because if you have 3 elements in a node, then you're going to have 4 children. So if we take M to be the maximum number of children, then we can guarantee that the height of our tree is always going to be between log base M of n and log base 2 of n. The nicest case will be if every node has 3 elements in it, and the worst case would be if every node just has 1 element in it and 2 children. But in that case, it operates the same as a typical binary search tree. So we still get log performance, which is what we want. And in terms of the performance for the operation you do when you split nodes, the maximum size of a chain reaction that you could cause by inserting a single element is just the height of the tree, right? Because you might have to propagate from one leaf all the way up to the root and make a new root, but that's just going to be roughly the height of your tree. Or in our case, that's just logarithmic in n. So we're getting good log performance out of our tree, and our tree is perfectly balanced. Any questions? Yes? Sure. So why not, you're saying why not? Why not take the U out? We choose Q essentially because we want to follow the same process that we've come up with previously. We want to apply the same process that we were able to apply to internal nodes to the root as well, to not complicate our code. You could probably tweak this idea a little bit and come up with some examples that might increase your performance a little bit in the short term, but in the long run, it won't have any major improvements over this runtime, which is guaranteed to be logarithmic. Yeah. What happens if you do a splitting tree where m is 1? Yeah, I think that would just look like a typical binary search tree. Yeah. Or actually, would it? Yeah, I think so. So here's 2 example trees of this idea that you could have where we're just choosing different values of m for the max number of children. So here's a tree where if m is 4, then you can have at most 4 children for any node and 3 items per node. Here's another kind of tree. Here's another kind of tree where m is equal to 3, where you can have at most 3 children, and each node can only have 2 elements. Now, splitting tree is sort of a nice name for these because that's what we're doing in our code. We're splitting nodes as we insert elements, but I didn't invent them, so we have to use their real name, which is called B trees. And we say that a B tree of order m equals 4, like the ones we use today, these are also called a 2-3-4 tree or a 2-4 tree. And that name refers to the fact that in a 2-3-4 tree, a node can either have 2, 3, or 4 children. And in a tree of order m equals 3, it's also called a 2-3 tree because you can have 2 or 3 children. And there's a quote from the ubiquitous B tree that says, "The origin of the name B tree has never been explained by the authors. As we shall see, balanced, broad, or bushy might apply. Others suggest that the B stands for Boeing. Because of his contributions, however, it seems appropriate to think of B trees as Bayer trees." So I guess Bayer was the name of the guy who invented them. Now, one last note on some terminology. So B trees are actually, this is more a note on their usage in general. So a note on the usage of B trees and their practicality. They are most often used in 2 contexts. When m is small, like we've discussed today, these are used as sort of a nice conceptual way to understand the logic behind B trees and how they work. And the other typical use for them is when m is very large. Let's say you make your m huge, thousands, and so every node can have thousands of children. This is often used in practice when you have database applications and file systems, systems where elements have very large number of records. And if you're interested, you can take CS186. Or perhaps, I know there were a couple groups that implemented a B tree on Project 2 as well. So pretty interesting, yeah. Now, since the small M tree that we've discussed today isn't too useful, as we'll see soon, people usually use B tree to just refer to the very large case. Are there any more questions on B trees? All right, then Daniel, you're up.
Hello? Can everyone hear me? Okay. Just bear with me just a sec while I get things straightened out the way I like it. Oh, God. All right. Almost there. Mirror displays. Okay. Cool. Okay, great. So my name's Dan. I'm going to take a quick detour into tree rotations. This is going to seem like it's coming out of nowhere, but we're going to connect this back to 2-3 trees in just a couple of slides. Okay? So when I'm talking about tree rotation, I'm talking about rotating a tree about a given node, left or right. Okay, so let's see an example. We got this tree over here. And maybe we'd like to rotate it left about a given node, G. So what we're going to do is we're going to take this node G, move it left, and then we're going to promote its right child in a way that seems natural. So let's see what that looks like. Okay? So as promised, we shoved G over, and we promoted P to be the new parent of our rotated node G. So it's like we grabbed G and P, and we yanked it over like a steering wheel. Okay? So it's important to note here that the semantics of our binary search tree that we just rotated haven't actually changed. Okay, all of the nodes are still in the appropriate place with respect to their ancestors. What I mean by that is A, B, C, G, K, J, L are still to the left of P, which is where they belong. Okay, so rotation of trees is a tool we're going to be using moving forward to manage the height of our binary search trees. Okay. And you can sort of get an intuition as to how that's going to work just by looking at this example. By performing a rotation left about the node G, we've actually decreased the height of our tree by 1. Okay? So if it's okay if it's not totally clear what's going on yet, because we're going to try an example. Okay? So let's say we're given this tree, which is the product of the rotation we just did on the previous slide. And let's say we want to rotate it right about this root node P, okay? So here's what we're going to do. We're going to follow the instructions. We're going to move P right, and that's what I'm going to do right here. And we're going to promote P's left child in a natural way. So here's what I'm going to do. I'm just going to drag G up over here. And now it's not really natural for G to have a parent pointer pointing to P, so I'm just going to go ahead and throw that link away. And like I said, P is the new right child of G, so we're going to reflect that over here by changing G's right parent pointer to be P. Okay, so now we have a problem. The tree rooted at K is floating off in space, right? So where are we going to connect K? What's the natural place to put it? Yeah, so the natural place to put it is right under P, okay? So let's see how we did. Take a look at the solution. And it looks like we came up with the right thing. Are there any questions so far? Okay, cool. So first of all, coincidentally, the rotation we just performed undid our first rotation. So we're right back where we started. Another important thing to note is that we actually bumped up the height of our tree by 1. So rotations don't always decrease the height of your tree. Sometimes they also increase the height of your tree. Okay? So 2 properties of rotations to keep in mind. They can shorten or lengthen your tree, and they preserve the search tree property of your tree. Okay? So over here we see one final example of a tree rotation. We're going to rotate this tree right about D, and we're going to promote B in its place, and we can see that all of the values in the subtrees are in the correct place with respect to their ancestors. Okay? Now here's a non-obvious fact. Given an arbitrarily, disgustingly unbalanced tree, there always exists a sequence of rotations that'll yield a balanced search tree. Okay? And it's by no means a straightforward problem finding such a sequence is, but we can use 2-3 trees to guide us to a working strategy. Okay? So that, oh yeah, question. This is my first time, so be gentle.
Can you define what a balanced search tree is?
Yeah, so a balanced search tree is, for our purposes going forward, I'm going to define it as a tree that's proportional to the logarithm of the number of nodes in the tree within a constant factor of 2. Okay. So the idea here is that we want our tree to be balanced in such a way that we're guaranteed to carry out any search and insertion operations in logarithmic time. Okay, so red-black trees. Red-black trees are sort of notorious for their difficulty, and that's kind of because the intuition behind red-black trees is not all that intuitive for students who are learning about them for the first time. But luckily for you, we just spent 50 minutes trying to get the intuition behind red-black trees within reach. So let's jump in. First of all, why red-black trees? Right? We just learned about 2-3 trees, and those are balanced. So what gives? Why are we even bothering? So the reason we're bothering is because 2-3 trees and 2-3-4 trees are both kind of a pain to implement. Maintaining different node types, conversion between nodes with variable numbers of children is a pain. You can see from the sample code, is 4 node, x dot split, make 3 node. It's kind of gnarly. So we don't want to mess with code like that. And another issue is that 2-3 trees will often involve walking up the height of your tree to split nodes. And that's no good because splitting nodes involves creation of objects, which, depending on the programming language you're using, can impose non-trivial overhead on the runtime of your program. Okay? Oh, and real quick, Donald Knuth said it. Beautiful algorithms are unfortunately not always the most useful. But that doesn't mean that we can't use 2-3 trees as a guide going forward. So here's the issue. 2-3 trees are slow and tricky to implement. And that's because it's a little painful to have nodes with variable, numbers of children. Okay? So here's a weird idea. What if we build some kind of binary search tree that corresponds or maps directly to the 2-3 tree that we introduced earlier in lecture? Okay? So here's a sample approach. What if we made some kind of red glue node, and we use this red glue node to glue together M and Q into the corresponding 3 node up here in the 2-3 tree. Let me just get some nomenclature out of the way. This is a 3 node because this node has 3 children. Okay. Likewise, a 2 node would be a node with 1 value and 2 children. Oh, let me turn on my nice laser pointer. Isn't that cool? Josh who, right? Okay. So that approach isn't terribly great because it wastes links and the code gets a little weird, right? Here's a second approach. What if we connected two nodes that are supposed to stick together in our 2-3 tree using some kind of red glue link? Okay? So I realize this is like a strange idea, but it turns out that this is the idea that's actually used in practice. Okay, so if you take a look at the Java standard library, this is actually how the tree set that lives there is done. Okay, and for simplicity, we're always going to map 3 nodes in our 2-3 trees to red links that lean to the left. Okay, so it wouldn't be correct to have a red link over here on the right. And you can sort of see the analogy here. Just as this 3 node has 3 edges coming out of it, this set of 2 nodes has 3 edges departing the component. Okay? And once again, this red edge represents the glue that sticks together these 2 nodes in the 2-3 tree node. Okay? So I just kind of asked you to swallow a sort of strange abstraction. And with a few examples, you should become a little more comfortable with what I'm talking about. But for now, let me introduce the left-leaning red-black tree. So the left-leaning red-black tree is a binary search tree where the edges are colored that's subject to the following rules. Okay, so no node is allowed to have 2 links. And why is that? Well, we said that the red link represents the glue that holds the nodes in our 2-3 trees 3 nodes together. So if we have two red edges coming out of one node, then that would be as though we had 3 nodes within a single 2-3 tree node. And the problem there is 2-3 tree nodes can have at most 2 values. So we're going to say that our analogous left-leaning red-black tree is only going to have 1 red link per node. Okay? Another rule is every path from root to leaf has the same number of black links, and red links lean left. Okay? So the idea behind this second rule here is it imposes some sort of balance on our left-leaning red-black tree. Okay? So you can think of the black edges in our left-leaning red-black tree as connecting the 2-3 nodes in our 2-3 tree. Okay? So in our 2-3 tree, we have a black edge connecting the M and EJ components. Likewise, we have a black edge connecting M and the 2 glued together components that represent that 3 node over here in the 2-3 tree. Now, because the 2-3 tree is balanced on black edges, that means the left-leaning red-black tree is also going to be balanced on black edges. Okay, so let's try an example. I'm not going to ask you to write this one out because we're running a little low on time. So I'll just show it to you. We're going to decompose the 3 nodes, UW, AS, AX, into glued together red-black tree nodes, and that's all there is to it. Are there any questions so far? Yeah. Yeah, so I guess you're asking, if we're allowed to have these red nodes, isn't our tree kind of expanding in height anyway? So the reason that's not such a terrible issue is because we're actually constraining the number of red edges we use on any given path from the roots to the bottom of the tree. So let me try to show you what I mean. So we're balanced on black edges, but you say the problem is, well, what about the red edges? So because the red links, because no 2 nodes, or rather, because no 3 nodes are allowed to be connected by 2 red links, because that would form a node that's too juicy in the corresponding 2-3 tree, we can't actually have 2 consecutive red nodes. So a result of that is you can have at most 1 red edge on a path for each black edge. And a result of that is that the height along any given path in the red-black tree can be at most twice the logarithm of the number of entries in the tree. Okay. Okay. so searching an LLRB tree for a key is actually relatively easy because these red links don't actually come into play until we start performing insertions. For the purposes of searching in our left-leaning red-black tree, they're going to behave just like black edges. Okay, so here's some facts of interest. It turns out that for any 2-3 tree, a data structure that's balanced, there exists a corresponding red-black tree that has depth of no more than 2 times the depth of the 2-3 tree. And with a huge dose of cleverness, let me back up. So the issue here is, how do we perform insertions, right? We talked about how to search for a key in a left-leaning red-black tree, but the question now becomes, how do we insert into a left-leaning red-black tree and still respect all the nice invariants here that promote balance in our left-leaning red-black tree, okay? So the answer is we're going to use the 2-3 tree as a guide toward performing insertions. So this is a rather advanced topic, and I actually don't have time to talk about it. And you don't need to memorize the rules that follow this slide, so I'm going to skip it here. You can find information about this in the guide. I realize that this sounds like insanely boring, but it's actually like crazy cool. So I recommend you come back and take a look when you have some free time. And that's all we have time for today. If you have any questions, please come to the front. And at your convenience, you can pour over the summary.